All right, everyone, here's a quick and dirty review of solving the wave equation for a guitar string. Many of you who land on this page will be interested in guitars, but not so interested in mathematics. I was going to say advanced mathematics or heavy calculus or whatever, but the truth is this is intermediate level mathematics, right? The prerequisites of really getting to the bottom of this are differential equations. However, I plan to deal with this in a very lighthearted way for anybody to watch and kind of enjoy how the process of solving this mathematical problem is done. So a deep understanding of mathematics isn't required to gain something from this. It certainly will be required to follow it, but in the end, I'm still going to give a equation that you can use to solve for exactly the shape of your guitar string at any time t after it's plucked, and at any position x between the nut and the bridge, right? So even if you don't follow the mathematical derivation, in the end, you will get a formula that can do exactly what we're after. We want to know the vertical displacement, right? The vertical displacement of every part of the string, every point. Sometimes it'll be displacement below equilibrium. I've drawn equilibrium here as a line, right? But the string can be entirely above equilibrium, right? In fact, it starts that way when you pluck it. We're going to see that our process involves picking an initial condition. And that initial condition, with exaggerated, will be like this, right? Will be the pick right here, suspending the entire string away from equilibrium, right? So presumably when you release it, that's at this time 0, you have a shape. And when you release it, the question is what shape exactly does the string maintain at any time after you release it, at any point along the string? And we're going to be able to answer that question for your guitar string. So even if you don't follow the full derivation, you should be able to capture you should be able at the end do the calculation. Okay, so let's begin. The first thing is we will articulate exactly what we're after. We're after this object that we're going to call U, just because it's sort of standard in the subject to use U. Not totally standard, but we'll use U. And U is a function. So if I tell the function the position of the string I'm interested in and the time, this thing is going to tell me the vertical displacement, right? So that means if I pick one time, say a millisecond after the string, that's a thousandth of a second after I release the string. If I fix that time and I start changing x from 0 at the nut x equals 0, and at the bridge, x will equal, and we'll call it L. And L is the scale length, right? So this will be the scale length of your guitar, which for all cool guitars is 25.5 inches, right? So you can pick any number for x between 0 and 25.5 inches, and you plug that number in here and 1 millisecond in there, and then when you crunch it, this is like a little machine, and when it crunches, it gives you an answer, and that answer is how far the string is displaced above or below the equilibrium. If it's a negative number, it's below the equilibrium. If it's a positive number, it's above the equilibrium. So that's our goal. Our goal is to find this function. And this function takes two inputs, two variables, x and t. And we've already discovered in a previous exercise studying the guitar string, we know how this object must be constrained by nature, by Newton's laws, right? We kind of worked that out, right? We used Newton's laws and a series of critical assumptions. And those critical assumptions were that this displacement h, the displacement of the string at any time is much, much smaller than the scale length of the string, right? So the displacement u, when we calculate a u, we get something we call u. That displacement divided by the scale length has got to be a number much smaller than 1, right? And it's also got to be true that the angle of the string at any point, right? The string, if you blow this up, you'll see the string has an angle here, it has an angle here, has an angle here. Those angles off the horizontal, which I guess I should make my thing a little skinnier. These angles off the horizontal which we might call theta, have to be small enough that we can say that these trigonometric functions, sine of theta equals theta, and the tangent of theta, these are trigonometric functions, must equal theta, and then the cosine of theta is approximately equal to 1. All of these things are approximations, right? It is never really true that the the sine of theta equals theta, and the tangent of theta equals theta, and the cosine of theta, the cosine of theta equals 1. That's never going to be true for any real value of theta. But when theta is small, these things are true. And we're going to define a small theta such that they're true. So theta is small enough that we're happy with these approximations. And between Newton's laws and these assumptions, we end up with the wave equation. Ta-da, the wave equation. We derived this before. And C is the tension in the string divided by the mass density of the string, which we take to be a constant. If C was not a constant, the mass density was changing, or you start changing the tension, like for example with a Floyd-Rose bridge, right? You get on the whammy bar. All this is out the window as soon as this stuff becomes variable. If this becomes a variable, then this equation here is no longer a linear equation. And if it fails to be linear, our solution is wrong, right? So failure to be linear, if that is a function of the length along the string from the nut. For example, if the mass density of your string, for some reason, if your string was very, very thick and heavy over here and it got thinner and thinner over there, that would be a problem. Although you might be able to save it. It's possible to save it. For example, if it changed in a very linear way, you might be able to figure something out. But if it changes in some random weird way, you're doomed. Well, this technique is doomed. Of course, you can figure these things out, but this technique is doomed. And the tension, of course, has got to be constant while the string is in motion. If the tension changes, then the dynamics of the system change. So, but assuming that, and that's an important assumption, but we do assume it, we take it to be face value, and we take the assumption about small theta and all that, and we end up with this beautiful equation. And what this basically says is the acceleration of any point on the string is related to the way the shape of the string is changing, and the proportionality of that relationship is c squared, where c is ultimately essentially the speed of sound on the string, right? And this equation is what we need to solve, because what we're after is u of x and t. I give you t, I give you x, and I get a number that's the displacement. I get out a number. It's that simple. I give it two numbers and it gives me one number back. And I need to find that expression. So how do we begin to solve an equation like this? First of all, this is called a partial differential equation. And if you're an undergraduate student of mathematics, say, you would learn about this, or probably in your sophomore year sometime. If you are studying physics or engineering, you'll learn about this in your first sort of mid-level course. You have to learn calculus. You have to get through your regular differential equations, which are called, by the way, ordinary differential equations. And you have to learn ordinary differential equations first, and then you can learn partial differential equations. And you'll see why. Because what we're going to do is we're going to take this guy and turn this partial differential equation into an ordinary differential equation. The reason it's a partial differential equation is because you're taking these derivatives with different variables. You have two variables here. You have x and t. It's not like I give you a number and you give me it's not like I give you a number, u meaning the function u, and it gives me a number back. I have to give it two numbers. And this function can change with respect to one of those numbers or the other, or both. And so I have to keep track of those changes separately. And that is what makes it a partial differential equation. So to solve this partial differential equation, we need to find every possible value of u, every possible function of u, such that when I take its second derivative with respect to time, and I multiply, and I take its second derivative with respect to space, and I multiply the second derivative with respect to space times c squared, I get the second derivative with respect to time. I need to know all the functions in the world that do that. And the problem is there are many. There are many, many solutions. There's an infinity of solutions. We have to go into this infinity of solutions. First of all, we have to find all the infinity of solutions. It's not like anything will solve it, but the number of things that solve it is infinite. We have to go into this infinity of solutions and then pull out the one unique solution, the solution that represents the motion of our particular guitar string in our particular circumstances. And that one unique solution is dipping into this pool of infinite solutions. So we got two steps. We got to find all the solutions, and then we got to find our solution. So let's begin. The first thing we're going to do is we're going to take a look at U of X and T and say, wouldn't it be nice if it turned out that this solution was actually the product of two slightly easier functions, X of X and T of T, right? So what we're going to pretend is that whatever this answer is, and we don't know what the answer is, but it's going to be separable into two separate parts that can be multiplied together. And one part only depends on the position from the nut of the guitar, right? That's what X is. Remember, X is the distance from the nut and towards the bridge, right? And this part only depends on X. And then the other part of the function only depends on the time that you're interested in. If I'm interested in the shape of the string at 3 milliseconds after plucking, this part of the function only depends on that time. Now, it seems weird. Like I have a mathematical expression that I need to solve. I have a mathematical equation that needs an answer. And the answer to this equation is a little machine that tells me the displacement of my string. A little function is the mathematical word for it. So, but I'm pretending that it can be described like this. That seems like an awful big assumption. And it is. It's a guess, right? This ultimately is a guess. There is interesting thing about mathematics at this level is there's very, very few. It's not like algebra where you can be taught a process and it will always work. That's not the case once you start getting into these kinds of physical models. At that point, it's more of an art form. And back in the day, in the 1800s sometime, or maybe even earlier possibly, the man who figured this out in the beginning was a guy named D'Alembert, although he used a different solution. Ultimately, the initial attack on this is some kind of insight or a guess. And it turns out this insight or guess is correct. It is true that every solution to this expression can be written in this form, separated. So with that in mind, we're going to take this separated solution and put it into our equation and see what happens. So the way we do that is we're now going to take the second, I'm going to look at the left-hand side, the second derivative of u, where I replace u by x times t, right? So x times t. I've eliminated this little x and this little t. We just know that x is a function only of the distance from the nut, and t is a function only of time. We just have to remember that. Well, x is not dependent on time at all. So it turns out you can pull that out, and then you can look at just the second derivative of t with respect to time. But what's interesting about this is that t is only a function of time, right? So it's no longer a partial derivative. It's now what we call an ordinary derivative. So we take this partial derivative and we change it to an ordinary derivative that is symbolized by the little letter d instead of this sort of Greeky looking partial thing. And now we have an ordinary derivative, and we can even give that a little bit of a nice easy notation and put 2 dots for the second ordinary derivative of t with respect to time. So now that we've done the left-hand side, we do the right-hand side. Again, we substitute xt for u because that's our assumption here. And now we know that t is not a function of x, so t comes out. And this will end up being c squared t times the second partial derivative of x with respect to to respect to the distance x. Remember, this is a little x here, and that's a big X there. This is a little x in the denominator of this operator. And we're going to write that as c squared. Remember, c contains the tension and the mass density of the string. So that's where the characteristics of our string are. They're sort of embedded in c squared. And that's times t. And then this becomes x double prime, where double prime means the second ordinary derivative with respect to the distance from the nut, which means, again, I can get rid of these partial derivatives here and change them to ordinary derivatives, right? Okay, so now we have calculated the left-hand side and we've calculated the right-hand side, but the left-hand side is supposed to equal the right-hand side. So this is supposed to equal that, right? These two are supposed to be equal. So if we were to write that down, we would be writing down x t double dot equals c squared t x double prime. And this now is sort of this is the direct implication of our assumption, right? We assumed this, right? And the direct implication of that, plus the wave equation, which we know is what governs our string, gives us this, right? This now is where we're at. This is what we have to work on. All right, so what do we do with this thing? Well, what we do is we look at it carefully and we say, I wonder, is it possible that we could get everything that depends on time on the left and everything that depends on space on the right? And it's actually quite easy. If you divide this equation by the function x and then divide it by t, this is exactly what happens. You end up with, I'll do it in black here, you end up with t double dot equals c squared t x double dot divided by x, and then you divide both sides by t, and this t goes away, and it ends up down here, right? So the final expression is this. You got t double dot over t equals c squared x double prime over x. And now is sort of where the magic happens, right? This is a technique that's called separation of variables. And the reason we call the technique the separation of variables is because everything on the left is a function of time, and everything on the right is a function of x. In fact, the second derivative of t with respect to time is still a function of t. T was defined to be a function of time. The second derivative of x with respect to the spatial variable x is a function of x, and x itself is a function of x. The point is that these two sides are always going to be equal, right? That equal sign never goes away. So we have this weird condition where the right-hand side is a function of x and the left-hand side is a function of t, but they're always equal. No matter what value of t I choose, this side will always equal this side no matter what value of x I choose. And that seems strange because I can choose x to be anything from 0 to 25.5 inches. And I can choose t to be anything from 0 to infinity. I can study the motion of my string at any time after I let it go, assuming I let it go at time t equals 0, right? Where this is measured in, say, seconds, right? So the only way this is possible is if the dependence on x somehow cancels out when you form this ratio. And so these two things must both equal one number, one constant. And that constant, that has to be the case, that these two things equal a single constant, because if it didn't, then when I changed x and held t the same, this would change and that wouldn't, and it would break the equality. So it must be that these ratios of these functions has to be a constant. So because of that, I can now write this in as two separate expressions. And that's the whole magic here, right? I write t double prime over t equals a constant. And then I write c squared x double prime over x equals a constant. Wait, one thing I want to do though. One thing I want to do. See this c squared here? The c squared? I want that c squared on this side, right? C squared, c is equal to the tension over the mass density. And this has to do with the vibration. Obviously, even as a guitarist, you know, the tenser the guitar, the higher the pitch is, which has to do with how fast it's vibrating. So we want things that have to do with time. It's probably best to keep them on this side, right? So let's keep them on that side. This is the dynamics of things. This is the shape of the string. This is the sort of the timed dependency of the string. So I'm going to erase the c squared here, and I'm going to write it on this side as 1 minus 1 over c squared. So I'm going to write 1 over c squared is a constant, and I'm going to write x prime over x is a constant. And it's important to remember, of course, that this is the same constant, right? This can only equal one number. But I can split this up into two different expressions. Obviously, they're tied together by this constant. But nevertheless, they're still quite independent. So I have to pick a symbol for this constant. I don't want, mathematicians don't run around with big words like constant in their equations, right? So I'm going to give this constant a mathematical name. And I'm going to choose that mathematical name to be minus lambda squared. And it is the habit of mathematicians to choose the names of these constants in a way that becomes convenient. So what have I done? Well, the constant is just some number, right? This is equal to the constant, right? So if this can be any constant, say, we don't know what it is, but I'm restricting the constant to be less than 0. And the reason is whatever I pick for lambda, when I square it, it'll be positive. And then when I take the negative sign, it'll be negative. So this constant is now going to be less than 0. And I'm just picking it that way because I can really pick any value for the constant, right? So I've really not changed too much. I haven't constrained things too much. I definitely want to keep an eye on it, but for now, this is good. So this guy is, we've now got two of these expressions. And what do we do with them? Well, let's look at the first one, right? Let's look at this one here. Let's look at this one here first. It doesn't really matter, but we'll look at this one here first. Let's write this as an ordinary differential equation. And the way we do that is we say it's x double double prime, right, equals minus lambda squared x. And then I write x double prime plus lambda squared x equals 0. And that is an ordinary differential equation, an ODE. And it's an easy one, right? It's easy. If you've studied this subject, you can look at that right away and probably assert what the answer is, what the solution for x. Remember, we're looking for a function x, right? And we can look at this, and those trained in solving ODEs, that's like this ODE is kind of like the 1 plus 1 equals 2 of ODEs, right? So that is a nice and easy answer. Then the other one is very similar. Oh, this is a double dot. Yeah, I got the double dot there. So we write the second one is going to be t double dot equals minus lambda squared c squared t. And I guess I didn't need to write it that high. For some reason, I thought there might be a denominator involved, but there's none. And then, of course, this becomes simply t double dot plus lambda squared c squared t equals 0. And that is also an easy ODE, which we can solve by inspection. By inspection means I just need to look at it and I can solve it because it's so familiar, right? For those of you who it's not familiar, that's just a goal of learning ordinary differential equations. And once you start learning ordinary differential equations, probably within the first few hours, you'll learn how to solve this guy. Okay, so I have these two ordinary differential equations. If I solve them, I know x and I know t. And remember, our answer, the thing we're looking for, is u of x and t, which is x of x multiplied by t of t. So I'm very close to getting my answer, right? Because I can solve this by inspection. I can solve that by inspection. I get this. I multiply them together, and I've got you, right? Well, kind of, yes. That is kind of right, but there's a long way to go. So let's now solve these things by inspection and develop an expression for you. All right, so here is our first expression, and as I promised, the answer for what x is x of x is going to equal a, some number a constant, times the sine of lambda x plus b times the cosine of lambda x, right? So the solution for x is the sum of these two trigonometric functions, where this constant lambda appears as a prefactor for x and this constant lambda in both of the trigonometric functions. And you have two numbers, a and b. These are numbers, right? These are just regular numbers, like real numbers, right? And they could be anything, right? They could be anything. So the problem is yes, I have found the answer to our expression, but I've got an infinite number of answers because I can choose anything for lambda, and this will still solve this equation. And I can choose anything for a and b. So I have three anythings, right? So I've just found an infinite number of solutions for x. But that's really the best I can do right now. So let's move on and let's do the same thing for t. Well, there's the differential equation for t, and the solution for t is actually very similar. It is going to be, I'll start with its constant d. It's the same, it's basically the same expression, right? But instead of just lambda, I now have lambda c times time plus the constant e times the cosine of lambda c times time, right? So I have the same solution because it's essentially the same equation. The only difference is here I only have a lambda squared, and here I have a lambda squared c squared. And you'll notice why we like to call this lambda squared is because the square root, whatever's here, the square root lands inside the argument of sine. So it's, if you start everything by being squared, then you end up with things that are not squared inside these arguments, right? Because back here in the very beginning of the wave equation, right, where is the first wave equation? I could have written this. I didn't need to define c as the square root of t over m and then throw a c squared here. I could just have put, t over m, or if I wanted just to make it simple, I could have just put c there. But if I had done that, then over here, I would have ended up with the sine of lambda times the square root of c t, right? Because that would have been a regular c, right? So to avoid all that, that's one of the reasons we define everything the way we do. It's just because we kind of know how this ends up because it's been done for hundreds of years. Maybe the first time they did it, they actually did have a little square root of c there, and then they refined it so you don't land with funny square roots of c's in your trigonometric functions. It's all a matter of form. But the point is we have the exact same problem. We've solved for t, and this t will always solve this differential equation, but there's an infinite number of them, right? I can pick any d I want, I can pick any e I want, and any lambda I want. And for that matter, I can pick the square root of the tension over the mass density, which equals c. I can pick any value of that, right? But this, however, remember, I'm working on a guitar string, so I should be able to figure that out from the layout of my guitar string, right? In other words, I control the tension, and I buy strings with a specific known mass density as reported by the manufacturer. So I can control C. So you might ask, well, if I can control C and take away that arbitrariness, is there anything I can control to figure out what lambda and what d and what e and what a and what b are? Because remember, there's now an infinity number of solutions, right? There's, with all these solutions solving the wave equation, only one of them solves it for my string. So the problem now becomes, I need to figure out, of all the values of a that are allowed, and there's an infinite number of them, which one of those values of a is appropriate for my guitar string. And same with B and D and E and lambda, which appears all over the place. There's only one value of lambda too that works for my guitar string. But regardless, even if I don't choose those numbers, if I take this and multiply by this, I will end up with an expression for u. And so let's write that down. And here it is. U of x and t, this guy right here, u of x and t, that's what we're after. It's x times t based on our guess and assumption from the beginning. And this is what we know to be x. And notice it's only a function of x. It's only a function of the distance from the nut. And this is only a function of, this is only a function of t, the amount of time after the string is plucked. So this function for u, if I put it into the wave equation, right, if I go d squared u dt squared, I will discover that every single time it will always equal du squared dx squared. I will always get that expression to be true using this. And now the problem is to find the value of a, b, d, and e, and lambda that solve it for our guitar string. So let's now dig into this bin of infinite solutions and find the one that works for our guitar. All right, so here is our solution. And one thing we haven't done is we haven't talked about the string itself, right? In the beginning, we kind of laid the foundation for what we want our string to look like. It's got a nut and a bridge, right? And we decided that the length of the string was going to be L. That's the scale length, right? And although we're expecting our scale length to be 25.5 inches when we finally get to the end here, we're going to, for right now, just say the scale length is this number L. And you could, in principle, change L to be, some Les Paul guitar scale length. And we also said that in the beginning, the string is going to have a specific shape, right? The string is going to kind of look like this. There's going to be some displacement from equilibrium at the start, right? This is your pick right here, right? Your pick is holding up the string, and that displacement is going to be a distance h from equilibrium, and the string itself is going to fall into a straight line up to this point and then a straight line down. The other thing we need to know about this is how far from the nut do we execute the picking motion? And that distance we're going to call P, right? The distance from the nut to the place you pick, we're going to call P, right? So these are things that set up our problem, because of all these millions of solutions, notice that we did nothing about the actual guitar string was part of this. This is any mathematical solution for our wave equation. We now got to force this thing to model our string. So we now need to sort of provide information about the string itself and get that information into this big bin of solutions. And the way that information lands is its values for A, B, D, E, and lambda, right? Those values are the equivalent of telling this equation or telling this answer for u, which of all the possible functions u in the universe that solve the wave equation, which one applies to the guitar string? And the answer is in the form of picking A, B, D, and E. So let's focus first of all on the nut and the bridge, right? The nut and the bridge. What do we mean by the nut? Well, what we mean is that whatever time it is, it doesn't matter what time it is, right? The displacement here at the nut, right? The displacement of the string at the nut, that means the string's motion above and below equilibrium at the nut is 0. The string doesn't move at the nut, right? The string never moves. So u at the nut must always be 0. So that's the same thing as saying that u at a distance of 0 from the nut for any time t, right, must equal 0. All right? So that is an important piece of information about u. And that piece of information does not apply to this general u. It is not true that that will always be the case for this general expression for u, right? This is the general u of x and t that always solves the wave equation. But we know that for any time t, whatever this is, it must always be 0. So if we plugged in any time, we would end up, this is the only part that depends on time. So this part, just we put in t standing for any time, and it looks just like it does right here. But this part is only referring to the position x equals 0. So I can actually dig into this and replace those with, place x with 0 here and study what's left behind. And I do that, and I just write this as lambda of 0. Let me put that 0 in with a color. And then I put this in as cosine of lambda times 0, right? And this now represents abstractly the value of u of x and t. Oh, I guess I could actually go over here, right? And I could erase this, and I could write u of 0 and t equals that, right? I could do that. And this now is an expression, an abstract expression of the displacement of this point at any time. But we know what that displacement is. It must be 0. Well, the sine of 0 is always 0. So this term here automatically becomes 0 no matter what, right? Because the sine of 0 is 0. But the cosine of 0, because remember, 0 times lambda is 0. So the cosine of 0 is always equal to 1. It's always equal to 1. So what we see then is that if this is equal to 1, this whole thing is 0. This whole thing equals b, right? So what this says is that the displacement at the nut of the string at any time is going to equal b times d sine lambda ct plus e cosine lambda ct. The problem is that this could take any value, right? So the only way this can be equal to 0 at the nut is if b equals 0. So we have now figured out that because we've constrained our function at the nut, we now know that b must be 0. Well, and that is important because now we can replace b everywhere we see it, which is only here, with 0. So this is what our expression looked like for the entire string, right? We go back to the full string expression, but we now know that b must be 0 in order to constrain our string at the nut for all time. So I will now erase this term, because if b is 0, the whole term goes away, right? And I will then move this guy out. And I don't need the braces anymore because there's only one little expression there. So now this expression is that I'm moving right now is what's left of our function, right? Our u of x of t now equals this. So we've simplified it by eliminating 1/2 of that expression. We didn't learn anything about a, but we definitely learned something about b. So now we're going to attack. So that was just using one boundary condition. We have another one. We have to worry about the bridge too. So now we constrain this thing at the bridge and see what does that tell us. Well, at the bridge, we now know that it's no longer x equals 0. It's now x equals L. But for any time t, that has to be 0, right? For x equals L at any time t. So now we go back to what's left of our general expression. And how does this thing, when x equals L, how do we make that always 0? Well, we have to understand the only thing the only place that x exists anymore is right there, right? So basically we have to write a sine times lambda, that's bad lambda times L, right? That's the replacement, and then this side is everything, right? That's all of this stuff, right? Well, this stuff, just as before, it could be any value because we just pick any number of t. This is true for all times t. So we can't narrow this down by selecting a value of t. So this just has to get put right in there. But this now is a number, right? Because lambda is a number. We don't know what it is. But that number times our scale length, if I take the sine of that number, multiply by a, then That is a number, and I take that number and I multiply by this thing. But this thing could be anything. So in order for u, well, let's see, wait, this is u of x of t, right? I haven't replaced x with L, but this is u of L of t, right? So in order for that to be 0 at all times, I need to find a value of, well, I could set a equals 0, right? A could be 0. The problem is if a is 0, then this solution is always 0, right? Because if a is 0, 0 times anything is 0, so it doesn't matter what time. Time goes away at that point because it just kills the entire expression. So if I set a to 0, this whole thing is always going to be 0. So that's no good. So because we know that there's a solution here that's not just a motionless string, right? So what we're looking for is the condition that sine of lambda L equals 0. And we know when the sine function equals 0 because we've studied trigonometry. In trigonometry, we study the sine function. It kind of looks like this. And we know that it's 0 when we know that this is the sine of theta, right? And we know that the sine of when theta equals 0, it's 0 when theta equals 0. It's 0 when theta equals pi, when it equals 2 pi and 3 pi and 4 pi and 5 pi. So in order for the sine lambda L to equal 0, lambda L must be one of these numbers. And it doesn't matter which number. It can be any one of those numbers. And sine pi L will equal 0. So we know L is our scale length. So the thing that we're choosing is lambda. And this is the requirement that lambda has to satisfy. Lambda has to be such that the sine of lambda times L equals 0. So lambda times L must be one of these numbers, right? Lambda has to be chosen so that the product of lambda and L is one of these numbers, 0, pi, 2 pi, 3 pi, 4 pi, in order to make it so that this is true. Not a hard thing to do, right? Now all we have to do is pick lambda to equal some number n, some integer n, times pi divided by L. And therefore, lambda L, right, if I multiply both sides by L, the L's will cancel and I'll get an n pi. And sine of n pi is always going to equal 0, right? So the point being that lambda has to be this special value of n pi over L. Now, pi over L we know, because we know the scale length, L. It's going to be 25.5 when we plug it in. Pi, of course, is a totally known number. And therefore, lambda is going to be only dependent on this number n. This number n. It can be any multiple. Basically, it's any multiple of pi over L, right? Can be lambda. Now, we're not going to choose n equals 0 because then, again, you would have the same problem as choosing a equals 0, right? This whole thing would be 0, and then the whole function would just be 0, and that's an uninteresting answer. But it is an answer, but it's an uninteresting answer. So we're only going to consider n equals 1, 2, 3, and on, and larger. So n is going to be 1. Let's see, hold on. N is going to be 1, 2, 3, forever and ever and ever to infinity, right? So we have an infinite number of choices for lambda, which doesn't seem like an improvement because I said the problem in the beginning was we can literally choose anything for lambda. But notice the language. Having an infinite number of choices, which is where we're at now, versus what I said before, where I said we can choose anything. We can choose any value or we have an infinite number of choices. This is not the same. I'm not going to kind of go into it, but this is an uncountable infinity, and this is actually, in our case here at least, it is a countable infinity, and that's different, and it's a huge improvement. It's a huge improvement. So now I'm going to insert this huge improvement into our expression, and we're going to tighten up u even more, right? We're going to, now we know what b was, we got rid of that, and now we kind of know what lambda is. All right, so let's clean that up. And here we have it, right? I've now inserted this n pi over L for lambda everywhere. And now you see here's where our c is, right? That's the speed of sound, the square root of the tension over the mass density, the string characteristic. And we've now beaten this back so that we have 1, 2, 3 unknown numbers, and we have n. So this is sort of a problem because I said the general solution for you, the overall solution, is this thing. But this thing depends on us choosing n. But what's important is it doesn't matter what n we choose, it will still be a solution for the wave equation. So when I write it down this way, I have to specify which n I'm talking about when I write down u. So this is no longer really an expression for our answer. This is just one possible answer, and I have to provide the number n here to identify which of the solutions. But now the good news is that of all the possible solutions to this equation, I now know that I'm dealing with a countable number of them. I'm dealing with u1 of x and t. I'm dealing with u2 of x and t. I'm dealing with u3 of x and t, etc., etc., etc. And I'm dealing with un, where n is some number, greater than 3 in this case, of x and t. And all of those are solutions. And each one is going to be different by its value of n and possibly its value of a, d, and e. We kind of haven't really figured that out, right? But we're just going to look at like one generic one and see if we can figure out what a, d, and e are. So that's our next step. But the other thing we need to remember about a partial differential equation is because it is linear, as we said earlier. Actually, maybe we didn't say it earlier, but if you look here at the expression for this is our wave equation right here, right, as we started out this lecture. You know, if c was not a constant, for example, if c depended on x or t, so if c was some function, if the speed of sound on the string was some function of time, like the string was losing mass or it had an uneven mass distribution or something like that, this would become what's called a nonlinear equation. As it is, it's a linear equation. And because it's a linear equation, what linear usually means is if you double the input, you double the output. If you multiply the input by an amount, the output gets multiplied by the same amount. The output is proportional to the input. But also, if you take the sum of if you take two different inputs and you sum them together, the output would be the sum of the inputs you would get had you put them in independently, right? Everything is proportional and just sort of adds up nicely. So the point is if I have any two, like I said, there's an infinite number of solutions for the wave equation. If I take any two of them, add them together, that sum is also a solution. And that's really important back here. It becomes critical to the solution of this problem. But if I take any of these solutions and add them up, right, I will get another solution, right? So in some way, but all the solutions must look like this, but any sum of them will also be a solution. So now I can write that the total solution is the general sum of all of these countable solutions. And the way I write that is this. I'm able to now say that the solution of the wave equation can always be expressed as the sum of each of these solutions, where these solutions are distinguished by n, a, d, and e. So now I need to figure out, I know n is easy to control. It's just we start at 1 and go to infinity, and we plug it in right here. So n is very easy. It's just a number. But a, d, and e we still need to work on. We've gotten rid of b already. So what's next for and we've used both boundary conditions. So now we have to go to a different set of instructions about the string. Remember, we asserted that the string had these boundary conditions at the nut and the bridge, and we used that boundary condition and we used this boundary condition, and from those we figured out the value of b and the value of lambda. So b was 0, lambda is some multiple of pi over L, some arbitrary multiple of pi over L. But what we didn't use, the fact is we didn't use this initial shape of the string. And we didn't use the fact that the string starts from rest, right? When we pick the string and we pull the string and displace the string, right? Once we displace the string and let it go, the moment before we let it go, the string is stationary. The string's not moving at all. So those two facts, the initial shape of the string and the fact that the initial velocity of the string is 0, we still have to use those. And those two facts are going to give us the rest of these constants. So let's first use the fact that the velocity of the string is 0. So the way we express this fact is we're going to say that we have to conclude that the partial derivative of un with respect to time, right? That's the velocity of any point on the string. That's how we write it in mathematical terms. We say the first derivative of this nth solution with respect to time, and that is a function of that velocity is a function of x and is a function of t. So we're talking correctly about the partial derivative with respect to t. But now what we're going to say is that when you examine this at t equals 0, right, this thing has got to be 0. So what I'm going to now do is take the derivative of this guy, set t equal to 0, and see what does it take, what choices for d, e, and a do I need to make to force that to be 0, right? So at time 0, the velocity of the string is 0. So first we take the derivative of this thing. Oh, I just noticed that I interchanged the cosine with the sine, right? Back here when I first did this analysis, d was the constant in front of sine and e was in front of cosine. Not a big deal, right? This is not a big change, right? So I'm going to leave it the way I've written it here. But this is immaterial. D is arbitrary, so I could switch the position of these and then rename d to e and e to d, and you get the same thing. There's no material change there. So, but the derivative of the cosine is minus the sine, so this is going to be minus d sine n pi c over L times t, and the derivative of sine is cosine plus e cosine n pi c over L times t, right? Now this thing has to be equal to 0 when t equals 0. So when t equals 0, this whole thing has to be 0. So if I substitute 0 here and 0 here, this guy goes away because the sine of 0 is 0, right? And 0 times n pi c over L, that's all 0. So that pi goes away. This part goes to 1, which leaves behind e. So and this of course is unaffected by the fact that t is 0, so that's just some number. So I have some number times e must equal 0, so I know that e must equal 0. Well, I've just nailed down yet another one of the mystery numbers. I've nailed down e equals 0, so I can now go back up here and if by setting e equal to 0, I've effectively eliminated this entire piece of the solution. So for our guitar string, that piece of the solution doesn't even exist. So we're now down to this. So now I can write it this way. Now there's one thing that's kind of important. Well, first of all, if you look at this, you see that d is a number that we still haven't figured out, and a is a number that we still haven't figured out. But if you look at it, d is just a factor. It's a number times cosine. This is a number times sine. I can actually take the d and I can move the d. I'm going to now slide it over there, and I move the d up front. And that's the same thing. But now I have a number I need to pick that I don't know, multiplied by a number that I need to pick that I don't know. It's still a number that I need to pick that I don't know. It's just divided into two pieces. So I can literally erase that and just rename that a. In other words, the constant d gets absorbed into the constant a. So because of the simplicity of this solution, I've actually lost having to worry about one of the constants. So this now is our solution, and it's looking really good at this point. I know C from the characteristics of the string. Remember, C was the square root of the tension over the mass density. I know pi. L is my scale length, which is something I know. I pick n to decide which of the infinite number of solutions I'm interested in. So the only thing left is I don't know A. The other thing that's important to understand is this is the nth solution. I pick n, and I figure out what this is, and I figure out what this is. But A is only valid for the nth solution, right? A needs a subscript n, because it's possible that if I choose U3, I'm going to get a different value of A than if I look at U2 or U5 or U50,000, right? So I can only pick A for each value of n. And that's really, really important, because remember what the overall solution looked like. The overall solution was this sum that we described right over here, right? I'm going to grab it and move it to the other side. Now, this is our overall solution. It's the sum of all these UNs. So what that really is that is going to actually be the sum from n equals 1 to infinity of some number an times the sine of n pi over L times x times the cosine of n pi c over L times t, right? And this sum is as close as we've gotten to a final answer. The only thing we don't know is for each choice of n, we don't know A. And we've kind of almost used up everything we know about our string. We used up the fact that the string's initial velocity was 0. That's the last one we used. We used the fact that the string was fixed at the nut and the bridge. What we haven't used up is the shape of the string at time t equals 0. So we now know that this expression here is our expression for the entire shape of the string at any time. So now if I write at time t equals 0, I write u x 0, I get the sum of a n sine n pi over L x, right? Because when I substitute 0 for this cosine becomes 1. So ux of 0, which is the shape of the string at time t equals 0, which is this shape right here, this initial shape, our plucked string displaced at a distance p, which, by the way, if I didn't mention it, I'm going to choose p to be 7/8 of L, right? So it should be right over or right in between the bridge pickup and the neck pickup. That's my estimate of where that is. And this is a pi here. And so that shape, this function of x, has got to be this shape, right? So that means this sum from n equals 1 to infinity has to add up to this shape, right? And the process of finding an is now very difficult comparative to what we've been doing, right? It's actually not that difficult, but compared to what we've been doing, this is a much harder problem, because now I have to find a whole bunch of sine functions whose only distinction is these n, this value of n, and I have to add them all up together with some coefficient in the front, some number that I multiply each individual one by in the front in such a way that they add up exactly to this shape in the very beginning at t equals 0. The process of doing this is called Fourier analysis. Fourier analysis is a much broader topic than just this. This is called the Fourier sine series, for what it's worth. And its process is pretty ingenious. We will not be going through it, but I will show you the calculation we use to get an expression for AN. Because remember, I need to know AN very precisely because I'm going to give you a distance on the string from the nut and a time, and this thing better return a single number. So all it takes is two things, and it gives me back that number, which is the height of the string. And when t equals 0, which is one of those choices for t, then I can take any point on the curve and I should map out this initial condition. But if I take any other time, right, if I take any other time t instead of 0, I take some time t, the string is going to have some other shape. And again, this function is just as confidently going to tell us what that other shape is. But in order to do that, I have to calculate unambiguously with absolute certainty what A is, and I'm getting that from this initial condition. So the way the math goes is it looks like this. And here you see it. This is the calculation for AN, and it starts innocently enough. This is a little bit of a sloppier calculation than it could be, mostly because I described the initial string in a way that was needlessly complicated, but it works. You use some basic calculus and you crunch through all this stuff and you end up right here with the answer. This is your answer for A sub n. It's this guy right here. And notice it's really nice. It's got number 2. H is the height of our pluck, right? And that height we're going to take to equal 1 millimeter, right? L is our string length. So L is going to be 0.6477 meters, which corresponds, let me get the thickness down. This corresponds to a scale length of 12.5 inches. C, in this case, it's funny, I used C to be the distance to the pluck as opposed to the P, which I use. So I guess I should rewrite this just so there's no confusion. This is actually P, and this is P. I think I used alpha for the speed of sound in this expression. So that's P. So P is going to be equal to 7/8 of the scale length. So it's going to be 7/8 times 0.6 times 0.6477 meters, right? So, and then N is what we choose to, we have to decide what N we're interested in. But again, we know L, like I said, so we know L, we know H, we know the number 2, we know the number pi. So we know everything in here to solve for AN once we pick the N we're interested in. So now with all this down, we can write down very close to our final answer. U of x of t equals this infinite sum, n equals 1 to infinity. And now I substitute all of this stuff in there. I write 2hl squared over p times l minus p, n squared, pi squared. And then this is just a number now. This is sine pi, n pi p over l, right? So that goes up here, sine n pi over L times P, right? So that goes up there. And then it's times the two functions of space and time, N pi over L x cosine N pi over L t. N pi over L t. And this is the verge of our answer. Of course, we have to substitute these numbers, right, that I told you about in here, and we'll do that in a moment. But this is going to be a number that only depends on n. But n, we count every single n. And what we know is that if we add up all of these n's, this infinite number of n's together, infinite number of u sub n's, right, each one of those is u sub n of x and t, we know that at time t equals 0, we will get this initial shape, right? This initial shape. And that initial shape is our last condition. But of course, we've run out of conditions, but we've also run out of unknowns because now we know everything. Oops, I forgot one number in here. This over here, it's cosine n pi L times c, the speed of sound, times t. So we do have to choose our tension and our mass density, though. We have to decide what's the physical characteristics of the string we're interested in. That's actually sort of it's an initial condition, but it never changes, right? The tension is constant and mu is constant. So we don't really call it an initial condition. But it is a condition because without it, you can't do what we want to do, which is input an x and input a t and solve this and get a displacement. So what do we use for the tension and what do we use for the mass density? Well, I'm going to choose a particular brand of string where I've learned from somebody who contacted the manufacturer some of the specifications. These are not secret specifications. I found these. I like these strings though, so I'm going to use the Ernie. We're going to use the Ernie Ball Power Slinky Low E. And from that, we know that with a tension of 85.87 newtons, which is 19.31 pounds, that's going to be our tension, right? And a mass density, these are the same number, right? This is just different units. And a mass density of 0.000422 pounds per inch, which is 7535 kilograms per meter, right, in metric. So that's our mass density, and that's our tension, which gives us a speed of sound c, which is the square root of t over mu. That's going to equal 106.75 meters per second, right? So that's the value for c. Now, pi over L is going to be 3.14, which is a pure number, divided by 0.6477, which equals 4.850. I've kept that little extra significant digits here, so this is, I'm being a little fast and loose with my significant digits, but this is definitely going in the right direction. So we know pi over L, and we know c, which means, God, do we have it finally? We know this and this and this, this and this. We know everything here, so we're done. We're done. We have actually solved this problem. So now we're going to write u of x and t out in its full numerical form. Also, I should note, another thing that's worth having a look at is if you look at u of x of t, if you look at this coefficient, what you see is that the closer you get to the bridge, meaning the closer you pick to the bridge, L minus P becomes a very, very tiny number, right? So if you pick, the closer you pick to the bridge, the smaller this L minus P term becomes. P will always approach the number 25, right? But as it gets to 25, this can become arbitrarily tiny. If you have a very small number in the denominator of something, right, notice that this denominator will get large if you have this whole fraction will get large if you have a small number in the denominator. N will stay the same, right? If you're looking at one particular term, pi doesn't change, and P can only be 25. It can't get any bigger than that. So the closer P gets to 25, this gets really, really tiny. And what happens is this becomes very, very big. So what that means is that you'll get larger numbers for larger values of n than you would if you picked in the center of the string. Right? If you picked in the center of the string, then you get the higher values of n, these numbers here will become proportionally smaller, which is kind of an interesting fact. Not super important right now. Let's write down the final expression with all of our numbers substituted. And voila, this is our final answer. You give me the length of the position on the string and the time after you release it, then you can solve for this, and you can solve for this, and you can solve for this, and you get a number. And you do this number for every n from 1 to infinity, and that will be the displacement of your string. This is it. Now, the thing that is so critical here to capture is that this term here, which this 517 number, that's called the angular frequency. The angular frequency is not the frequency you're used to. You're used to the regular frequency. And the regular frequency for the nth solution, the regular frequency for the nth solution is 2 pi times the angular frequency, which is usually given as an omega, the Greek letter omega, which looks like a W. And so if you set n equal to 1, the frequency of this string, the frequency, the real frequency of the U1 solution for x and t, that frequency is going to be 82.41 hertz, right? Which is about the tuning of a low E string, which is usually set at about 83. So, some approximation in the tension and the mass density, and our model is just a little bit flat from the 83 hertz. But this is the frequency, right? What do we mean by that? Well, if you look at this term, this cosine term oscillates in time, and it starts at t equals 0 from some, this cosine term oscillates like this in time, right? This drives the strings oscillate. Any one point, you fix x, and that x is going to go up and down at this particular frequency for this particular mode. You have to choose n. Don't forget you have to choose n, right? So the n determines the modes, and we don't confuse the word mode with Mixolydian and Lydian and all of those scale modes. Each of these is a mode of vibration, right? And each mode of vibration is shaped like a sine wave. That's the shape, and this is the oscillation. And each mode vibrates at a frequency equal to 2 pi times omega n, the angular frequency, times the number n, well, the omega 0, right, times the number n. And this is what gives us the harmonic series, right? This is the origin of the harmonic series. Each mode of vibration has a unique frequency, and that unique frequency is some multiple of 82.41 times, hertz, right? It's a multiple of 82.41 hertz. But there's an infinite number of them. There's an infinite number of them because you need an infinite number to get your initial condition on the string, right? To get this initial shape exactly right, you need an infinite number of modes. And each one of these modes is in music terms called a harmonic. But now notice, everything is very, very clean here, right? Each point moves up and down with a very specific frequency. Those frequencies are exact multiples of 82.41 hertz. And and there's no damping, right? There's no damping. In more advanced calculations, you discover that higher harmonics of the problem are not even multiples of some base harmonic, and you discover that damping exists, and sometimes the damping exists unevenly for the harmonics. So there's a lot more to be learned about a real world wave equation, but this is the answer. This is the answer that we were seeking. You give me the position on the string and the time, and then you run this calculation an infinite number of times, and you will get the displacement. And you can cut this off at some approximate value. And eventually these terms get very small because n grows, and this grows as the square of n. So by the time n is 100, right, the biggest this can ever be is 1, right? And that's a tiny number. This one, once it's 100, you're dividing it by 10,000. So this term gets really, really small. So you can truncate this calculation to some arbitrary precision that you want, and you can get your calculated shape of the string exactly right. Okay, so that completes the task of showing you how to calculate the exact shape of your guitar string at any time.